Okay, so the goal for this video is to work through Lab 1. So just in case you weren't able to complete Lab 1 successfully or had a little bit of trouble along the way, this should give you a pretty good, should get you caught up with Lab 1 and get you a pretty good start on Lab 2. So when we install Octave, we should have an icon that looks similar to this. We want to use the GUI, the GUI, Graphical User Interface option. And we should have a zipped folder that we downloaded from Blackboard. So the first thing we'll do is unzip the zipped folder. We'll just extract this also to the desktop. And we will pull this folder out onto the desktop here. And I'll delete that zip folder just so that I don't accidentally try to use programs that are still zipped that might interfere with Octave's ability to access those programs. And I see that I have some M files as well as a couple of files for the lab here. So let's open the PDF and take a look at what we want to do. So the first thing we want to do is just kind of check that Octave installed properly and so on by running some simple commands. So let's double click on the icon, open Octave up. We see on the bottom here we have the command window. We can navigate over to the editor, which we'll also use quite a bit. So going back and forth between these two is something that we'll do fairly often. We can perform some simple arithmetic computations, 3 plus 7. We can do something a little bit more involved. And again, this syntax and what I'm doing here will be a lot more familiar if you've already gone through the on-ramp. So hopefully you've gone through that to get somewhat used to the syntax and what all of this notation means. So we're setting up a list of numbers from 0 to 10, going by increments of 0.1. So this list x vector is a list of numbers from 0 up to 10 in increments of 0.1. We put this semicolon at the end so that we suppress this output because this kind of clutters up the screen. Our y vector, our y list of numbers, is just the squares of each of these numbers. We have to use this dot arithmetic to say that MATLAB or Octave is really meant to be a linear algebra program. So really it's thinking of these lists as vectors. And we have to say, what do you mean when you say that you want to, say, square a vector or multiply a vector by itself, right? That those aren't necessarily well-defined operations. So what we're saying here is, well, what I mean that I want you to do is I want you to take each element and square it. So we'll get a list, 0, 0.1 squared, 0.2 squared, and so on will be what yvec is holding. And then we can plot with plot xvec comma yvec. And we see a figure shows up. So that's good. We've confirmed it kind of seems like everything is working reasonably well with Octave. And we could go through a couple more checks as well. But I'll jump down to these instructions here. The next thing we want to do is we want to make use of some of these programs that we downloaded and unzipped. So we need to navigate to the proper folder. And we look over here on the left in this file browser menu. And we see our current folder is this one here, but I want to navigate to the desktop, which is where I have my Lab 1. I'll also navigate to Lab 1. And now I'm in this file path. And I have access to all of my my Euler and direction field scripts and functions. I also kind of see the PDF and the docx here, but obviously Octave isn't going to do a great job of opening those. When we're in Octave, we're going to be using these M files. So we'd like to run the df script file. And if I start typing and I hit tab, it will autocomplete if I've typed enough that the program can figure out which file I'm trying to run. So if I run df_script, I see I get this figure here that plots a direction field that's outlined in this file. If I double click this dfscript.m, it pops me over to the editor and shows me what I'm running. I'm running a piece of code to define the differential equation. So here we have y prime is 4y minus 3x over 2x minus y. The window that I want to use, x min to x max, y min to y max, is negative 10 to 10 on both. The resolution is 20 arrows in each direction, so 20 by 20 grid of arrows. The length of each arrow is 0.5. And then what we do is we call the df function with these inputs, this de, window, resolution, and length inputs. The df function is a function that essentially what it does is, here we go, it runs this piece of code, which is really the kind of main thing in this function. The rest of the stuff is just some other stuff to maybe make things look a little nicer or get things to work a little better or a little more the way that I would like them to work. But really what it does is it runs this quiver function, and this gives us that nice plot of the direction field. So again, you should go through, anytime you download new code, you should go through, get an idea of what it's doing, read the comments, understand how to use the code, understand what the inputs and the output or outputs are, etc. If we ever have trouble with code, if we try to run it and it doesn't seem to be running the way that we'd expect, it's a good idea to jump over to the command window. And if something was awry, if we had, let's just say we had maybe an argument missing here, and if we try to run this code, we see we get an error. And these error messages are very helpful. This tells us, okay, it tried to run dfscript, but this variable y is undefined near line 5, column 5, so maybe I run over to dfscript, line 5, column 5 is roughly here, and we say, oh, okay, maybe that was the mistake that I had. Now I run it, I do get my figure, so that's promising, and I can always, again, check my command window, and I note that this time when I ran it, I did not get any error messages pop up. So typically if you have multiple errors, you want to start with kind of the most obvious ones, clear the errors one at a time, clear one error, or at least attempt to fix that error, run it again and see if that error goes away. Typically you don't want to make 5 or 6 changes at once and then run it again, because sometimes one error can cascade into a bunch of other ones, and sometimes if you fix kind of the most obvious one, then a lot of the other ones, or maybe all of the other ones, go away. We can also run an Euler's method simulation by running eulerscript.m, and similarly euler.m is a function file. It takes some inputs, it yields some outputs, and it runs Euler's method. So again, I'll let you kind of read all of these details, but eulerscript.m sets up the inputs. The interval that we want to solve the differential equation over is 0 to 10. The initial condition, y of 0 at x equals 0, y equals 0.3. The step size we'll use is 0.05. And the value of k that we're going to use for this example, for this differential equation, is 2.5. Our differential equation as an anonymous function is this here, k times y times 1 minus y. And we're going to input all of these into the Euler function, and it's going to output a list of x's along with a list of estimates under Euler's method for y. So we have a list of, if we think of a table of values, we have a list of x's that are known and a list of y's that ideally we would like to know exactly, but we don't know exactly. But since we're using Euler's method, we're getting an approximation, so that list of y's is going to be a list of approximate y coordinates for those x coordinates for the actual function that solves that differential equation. So again, Euler.m is the function file, Euler script is the script file, and if we run Euler script, which we can do by clicking this little gear with the kind of play arrow, we can run it that way as well. We could run it by typing it into the command window, Euler_script, and hit enter, or we could run it with that play arrow. And we see we get a plot of an approximation to the solution. Again, always a good idea to check back at the command window, and we see it plotted out or printed out our differential equation, but we didn't get any errors or anything like that, so that's good. If we didn't want it to print out our differential equation each time, we could stick a semicolon in there if we wanted to suppress that output as well. And then we see that it didn't print that this time. I do like having it print this out just as kind of a reminder of which differential equation I'm working with, just in case I forgot to change it or something like that. Okay, so let's work on these couple of problems. So problem 1, we want to adapt df script to plot these direction fields. We want to make sure we use dot arithmetic, so that's just a good practice to get into. And let's start with this one, 10 minus 1/10 v squared, and that's dv dt. So we know that kind of v is associated with y here, t is associated with x here. So if I come over to dfscript.m, I need to change my differential equation. I want 10 minus 1/10, or 10 minus 0.1 times, and then I have dependent variable squared, y squared. I'm going to do a dot caret to the second power. Again, using dot arithmetic, just to be careful here. The window that I want is 0 to 5 for the independent variable, 8 to 12 for dependent. So let's come down here and change this to 0 to 5 and 8 to 12. Resolution, let's stick with 20 by 20. If it doesn't look that great, we can come back and change that and kind of replot it if we're not happy with how that looks. And same with length. We'll stick with 0.5 for now. We really should never have to change the df function, the direction field plotting function. What we'll change is we'll change the script, and then we'll call the function. So typically when we write a function, we write it once, we debug it, we check it very carefully. When we're happy with it, it just kind of sits there. We don't change it, and then we call that function using scripts. Now, of course, if I gave this function to you, so if you have a different taste or something, if you like the titles to be phrased differently or something, you could edit it to your liking if you chose to. But as a general rule, kind of once you make a function, that function kind of does what you need it to. You leave it alone, and then you call it using scripts with different inputs, like we're doing here. So let's try to run this and see what we get. And we get something that looks pretty reasonable. So we get a pretty nice looking direction field. We look at this and we note, okay, well, v prime is 10 minus 1/10 v squared. It seems like what v equals 100, or sorry, v equals 10, v squared is 100, v squared over 10 is 10, 10 minus 10 is 0. So when v equals 10, it seems like we have an equilibrium solution, and it looks like that here as well. It looks like kind of all roads are heading to that terminal velocity of 10 units. If we wanted to see that equilibrium solution a little more definitively, we note that for our y-axis resolution, our vertical axis resolution, we use 20, and it seems like we kind of split right here. Maybe if we change that to 21, maybe we get something that looks a little bit nicer. So let's just give that a try and see what that looks like. And we see that maybe now we're a little happier with this picture because we do see that equilibrium solution very nicely here. So here we might want to draw by hand some solution curves. So let's take a screen cap of this. There we go. Pop this into OneNote. And now I can, maybe draw in it. Maybe I can draw 3 different possible solution curves. It looks like the solution starting at height 10 will maybe follow that path. 0.8 and 0.12. 0.12, starting up here, it looks like we'll follow a path something like this. And then 0.8, starting down here, we'll follow a path maybe something like this. I always joke I'm certainly not an artist, so these of course are not expected to be perfect, but we are drawing our solution curve so that it kind of follows the trajectories of these arrows, as reasonably as we can do it by hand. And so this might be what we would do for the next 2 examples as well. X plus sine y, we would change the differential equation, we would change the window, we would plot it, get the direction field, take a screen grab, say, maybe put it into OneNote, something like that, and then plot a couple of solution curves. Okay, so problem 2, for each of these differential equations in problem 1, now we want to use Euler's method to solve the initial value problem on the specified interval. And we're going to start with a relatively large step size of 1 unit. Typically this is going to be too large to make us happy. And then we'll start cutting it by powers of 10 until we get to a point where cutting it by another factor of 10 doesn't really change the way that the picture looks. And then we might be pretty, at least qualitatively speaking, pretty satisfied that we probably have a picture that looks more or less like what the actual solution is. So let's, again, take a look at number 1 here, 10 minus 1/10 v squared, on the interval 0 to 5, with an initial velocity of 12 units. So I'm going to copy my differential equation here, and I'm going to move it over to my Euler script. So I'll replace this differential equation with that one. K is not doing anything, and now let's clean that up. It won't hurt anything if we leave it in there, but for completeness, maybe we'll clean it up. The interval is 0 to 5. The initial condition, I think, was 12, right? Let me just double check that. Yep, the initial condition was 12, solving on the interval 0 to 5. And we'll start with a step size of 1 and then start cutting it. So we'll start with an h of 1. And let's run this. And we see we get pretty terrible behavior, right? We know what our solutions more or less should look like, right? This solution should look like this. It should be a nice gentle exponential decay towards that terminal velocity of 10, but we get this crazy zigzag. What's going on here? Well, what's going on is we start out in the trajectory going this way, but taking a full unit step out, what ends up happening is, well, I don't know how that happened, but what ends up happening is we end up way overshooting. And we end up on the other side where we're now getting pushed back up. And then we take another step out in this direction, and again, we end up overshooting. So we're getting bounced back and forth. And that's just because we're taking too large of a step size, right? If we took a smaller step size, we'd be able to correct our trajectory as we go along. And that's what we'll see here as we start cutting the step size. So maybe I'll move this over just a little bit. I don't think I can move it too much more than that. But as I start cutting my step size to, say, 0.1, now all of a sudden I have much nicer behavior. I know this is more or less what it should look like. But let's cut to 0.01 just to follow the instructions precisely, and we see that we get really the same graph between 0.1 and 0.01 for the step size. So we're confident that this is a pretty reasonable approximation to the solution. And again, we would do a similar thing for equations 2 and 3 as well. Okay. So then the third problem, consider this differential equation, y prime equals y minus 3e to the negative 2t, y of 0 equals 1. And what is our goal here? Use Euler's with step size 1 to graph the approximate solution on 0 to 12. And then we want to repeat with these different step sizes. So we should have 4 graphs. It's probably a good idea to fix the window size, because otherwise, if your windows are all different sizes, it's hard to compare what's going on. And we want to address this question on the interval 0 to 12. For each of these different step sizes, where does it seem we have a good estimate versus a poor estimate? And then next we want to graph the actual solution. We can check that this is an actual solution. So we want to graph this actual solution along with the approximations for h equals 1 and h equals 10 to the minus 3. Okay, so let's work through this. So we have a differential equation, y minus 3e to the negative 2t, or what we'll call is y minus 3 exp is the exponential function, negative 2 times the independent variable here is x, not t, so we'll just call it x. If you wanted to, you could call it t and then change this to t, but I just like keeping x and y as the independent and dependent variable and then just switching those in my head. So we want to start with h equals 1, step size 1. And we want our solution interval to be 0 to 12. So 0 to 12. Our initial condition is y of 0 equals 1. So we'll change this to 1. Let's plot and see what we get. So paying particular attention to the axis over here, negative 2500 to 500, we get something that is an exponential growth away from 0. It just dive bombs down away from 0. Let's see what we get as we cut h. So what happens is when I go to, say, 0.1, I get a similar looking picture, but my axes are a little different. from negative 8,000 to positive 2,000. When I go 0.01, again, similar picture, but my axes are still tightening up a little more, negative 1,200 to 200. If I go to 0.001, I see I get from negative 120 to positive 20. So I can see that I'm getting my solution tightening up to this kind of zero horizontal asymptote, but it always seems to kind of break away and then, fall off a cliff, so to speak, after some point. So that's kind of the interesting thing about this problem is if we kind of look ahead a little bit, we know that the answer, the solution that we're trying to find with this numerical method is e to the negative 2t, which should start at 1 and decay to 0 very nicely and smoothly. It should not shoot off to negative infinity. But this is kind of a hard problem for Euler's method to solve. There are just some things about this problem that make it difficult to solve. It's very easy for Euler's method to kind of overshoot that y equals 0 kind of horizontal asymptote, and once it overshoots, then it kind of goes off to negative infinity. So before we saw it overshooting, but we were kind of overshot, and then we got shot back in the previous direction, so we had a zigzag. Here we're overshooting, but as soon as we overshoot, we kind of fall off a cliff. With h equals 10 to the minus 4, and this is the picture that we ended up with. I did try running it with h equals 10 to the minus 5, but with the I have screen recording software and everything running in the background, and I think it was just a little too much of an ask for my computer while it was doing all of the video editing and all of that, and it was taking a very long time to come up. So so this is what it looks like with 10 to the minus 4, but it's going to look pretty similar with 10 to the minus 5 in there for h. It's just going to come over much closer to the 12 on the horizontal axis before it starts to drop off. So the last bit for this problem is we want to graph the actual solution, e to the minus 2t, along with two of these approximate solutions. So I can use my Euler script here. I can use this template, or I can come over here to Euler script solution, and I see that what does this do? This has a differential equation, it has something that calls Euler's method, an actual solution, and then it plots them. So I can use this as a template to build off of, right? I can copy my differential equation over. So that's the differential equation I want to use. My x interval, y naught, and h I can copy over. I'm going to be changing h in a minute here, but we'll copy those for now. These don't come into play in this problem. They were for the other problem. Here I'm calling the Euler method with this differential equation, the x interval 0 to 12, y naught of 1, and then h here. I have an actual solution. What was it? E to the negative 2x in this case. So this is just going to be exp of negative 2 times x. Y actual will be the actual solution evaluated at x at the outputs from this Euler function up here. I'll plot my Euler estimate. This hold on says keep the same figure up, and then plot this over top of that same figure. And I'm going to plot x along with y actual, the actual solution, I'll plot in red, and then I'll hold off to free that figure up so that next time we plot we'll use a different figure. Now maybe here I'll use an h of, what was the one that I was looking for, h of 1. So I use an h of 1 here. Let's see what we get out of here. And what we get out is something that's not very helpful, right? we just get what looks like a flat red line, and then the blue curve is kind of what we were seeing before with these negative so many thousands up to positive 1,000 or something. So let's tighten up the axes here. So we can do axis, and then we'll set our x coordinates 0 to 12, seems reasonable, and our y coordinates, maybe let's try like -5 to +5. Let's take a look and see what that looks like. And that looks, okay, right? That looks a little better. We see our exponential decay here, although it's not a very smooth curve because we have h equals 1. We're going to fix that in just a minute, but we're taking incremental steps just to make sure everything is still running and all of that. And then we have our Euler estimate here, which, again, it overshoots and then it just kind of falls off a cliff. We've seen that behavior several times so far. But it does seem like everything is running and plotting properly. So what might I want to do to finish out this problem? Well, the first thing I need to do is I really need to do 2 Euler calls. One with h equals 1, one with h equals 10 to the minus 3. So what I might do is, instead of saying what h is right here, I might do, let's see, instead of h equals 1 up here, I'll just put h equals 1 directly in this line. And then I'll make a copy of this line. Oops. I want to come down a little further. I want to come down here. I'll make a copy of this line. So what am I doing? Figuring out my Euler estimate with a step size of 1. Then I'm plotting it. As we're getting a little more complex, maybe I'll rearrange some things just to keep things a little more orderly. So I have my kind of bad Euler estimate, then I plot it. I define my actual function. Maybe I will do that down here just before I plot that. So these 3 lines are defining my actual solution, evaluating that, so I have a list of x's and y's for my actual, and then plotting it in red. And then here I'm going to plot my better Euler solution, h equals 10 to the minus 3. So I'll type in 0.001, and I'll do the same thing that, I'll do the same thing I have up here, plot that. I'm reusing x and y here. Using the x that comes out of here, where my step size is 10 to the minus 3, is going to get me a nicer looking actual solution as well. This is, again, between these hold on and hold off, so it's going to hold, we're going to plot our bad Euler solution, hold that figure on, continue plotting on that same figure, our better Euler solution, as well as our actual solution. Now, there are many different ways to do this. You wouldn't have to, make the code kind of flow this nicely necessarily, but, this would be one approach. And let's hit the play button and cross our fingers, hope it works. And there we go. We have our actual solution, our bad Euler solution, and our better Euler solution. And just to bring this home, let's, for our better Euler solution, let's give it a different color. We have red here. For our better solution, maybe we use K for black. B stands for blue, so K is the letter for plotting it in black. So just so we can tell which one is which. And there we go. There's our bad Euler solution in blue, better Euler solution in black, actual solution in red. And we see that as we cut H, we're kind of tightening up to that red actual solution. Okay, so that should wrap us up for Lab 1. That should give you an idea of how to use all these programs, and the solution programs will also be posted, so that way you can run these on your own and you can use them in Lab 2 or in future labs where they might be helpful.